Okay, so there's one final property of relations that we want to talk about, and that's what it means for a relation to be transitive. So we can see that for all x, y, and z in our set X, for a relation to be transitive, we have that if x and y and z are in the relation, then we must also be able to find x, z in the relation. This idea is used a lot in everyday language. For instance, in sports, we do this type of thing for you guys out there who follow sports. So for instance, if you do something like this, if you say KU defeats K-State or something like that. I'm just making up teams that are local to us. KU defeats K-State, and also you know that K-State defeats what's another team? Let's say Colorado. So KU defeats K-State and K-State defeats Colorado. That should imply that KU is going to defeat Colorado. And so we do that type of thing when we talk about sports and football and basketball and things like that. And you might even use that type of logic not just in sports but in other things in your everyday life. And of course, if you follow sports, you know that type of thing doesn't always work. Every game is independent and you can't necessarily use that type of logic. But in a mathematical sense, that's exactly what we're talking about, where right in my definition, this would be K-State. Right? We had KU related to K-State, and the relationship was X defeats Y. Right? So KU defeats K-State and K-State defeats Colorado. Right? So when we're looking for transitive, the key thing to look for is that this second value in the ordered pair matches this first value in this other ordered pair. Right? So that K-State was common to both of those relations. Okay, so if we take defined on this set X, a more mathematical example, here is our relation, and we're going to determine whether or not that's transitive. Now, determining, it can take a long time to look through all of the different elements, excuse me, and determine whether or not this relation is transitive. But what we're looking for, again, any two elements, we're looking for any two elements in the relation where the second value of the first ordered pair matches the first value of the second ordered pair. So for instance, these two would be candidates, right? Because we have 1 related to 2 and 2 related to 3, right? So what we're looking for is we take these outside values. The question is, do we see 1, 3 also in the relation? And we don't. Right? So right there we can stop and we can say that this guy is not transitive. We can say that that's not transitive. And there's other examples that prove that this relation is not transitive. For example, if we look at this element and this element, we've got 3, 4, also 4, 1. So the question would be, is the element 3, 1 in the relation? And we look through and we see that 3, 1 is not in the relation. And so again, this is an example of a relation that is not transitive. Now, if you had a relation that was transitive, it would probably take a long time. You would have to go through and inspect every possible pairing of elements in the relation where you have this second value matching the first value, right? And then you'd have to make sure that also in the relation was an element with this value and this value here, right? So if you're given the elements of the relation, it could be very tedious and time consuming to verify that a relation is transitive, and that's probably not something we would really want to do. It would be much more practical to have you verify that a relation is not transitive. Now I'm going to look at another example here in just a minute, and we'll see that if we're given the specific relation, notice we're not, for this relation, we're just given the elements. Right? We're just given the elements. We're not told exactly what the relationship is. How is 1 related to 2 and how is 2 related to 3? We're not given the specific relationship, but if we were, then verifying that it was or was not transitive might be a little more practical. So let me go ahead and jump into that. Right, and here's what I mean by the relation being specified. If we're told that x is related to y specifically in this way when x is greater than y, and we're defining that on the set of positive integers, then we can let's go through and we'll look at each of the 4 properties of relations that we just introduced. So let's ask, is this relation reflexive? Basically what we're looking for, or what we're asking for this relation to be reflexive, is x related to itself? In other words, based on this specific relationship, we're asking, is it true that x is greater than x? And remember, we're looking at the set of positive integers. So, for example, would it be true to say that 1 is greater than 1? No, that's not true. Is 2 greater than 2? No, that's not true. Right, so we can see that's not true for any values of x. Right, so this is not reflexive. This relation is not reflexive. Okay, the second property we talked about was symmetric. And remember, essentially what we were looking at is that if we know xy is in the relation, or x is related to y, so I guess maybe if this, then also y is related to x. Right, this is a little if-then statement, so we could do a direct proof on this if it's true. So if we assume the if part, assume that xy is in the relation, right? Then what that means is that x is greater than y, right? But if x is greater than y, we're talking about the positive integers. If x is greater than y, then it's not possible for y to be greater than x, because we just said we're assuming that xy is in the relation, which means x has to be greater than y. We can't have it both ways, right? We're talking about positive integers, and so this element yx cannot be in the relation. So this guy is not symmetric. No, it's not symmetric. Now remember, if a relation is, most of the time, if we have a relation that is not symmetric, that means that it should be antisymmetric. So let's look at antisymmetric. So is the relation antisymmetric? I could put a question mark there. We don't know for sure. So let's see. For antisymmetric, we had if xy is in the relation and yx is in the relation, then x must equal y. Okay, well we just went through, when we verified that the relation was not symmetric, we just went through and verified that if we've got xy in the relation, it's not possible for yx to be in the relation at the same time, right? That means that the if part in the definition of antisymmetric is false, and in an if-then statement, if the if part is false, then the statement as a whole is true by default, right? So that definition is true by default, and so yes, this relation is antisymmetric. Okay, and then finally, is the relation transitive? And so remember, to be transitive, we had that if xy is in the relation and yx is in the relation, then xz must also be in the relation. Right, so if we're going to prove this, we can assume this is a little if-then statement. We can assume that xy and yx are in the relation. And what that means is that we have this, right, by the way the relation is defined, x is greater than y, and what this guy means is that, oh, I'm sorry, I got going a little too fast here. This guy needs to be z, right there, yz. And so this should be a z. That's not going to make any sense if it's an x. Right, so what this means, if that's in the relation, then y is greater than z. Right, so if you've got these at the same time, you've got x is greater than y, and at the same time y is greater than z. I mean, think about if you put some numbers in for x and y. Say, let's say something like 5 is greater than 3, and at the same time 3 is greater than 1, then of course you can conclude that 5 is greater than 1, right? Because you've got both of these at the same time. So this guy must be greater than this guy. So x is greater than z, and that means that xz is in the relation. So yes, this relation is transitive. So without doing formal proofs, that's a way to verify whether or not a relation is reflexive, symmetric, antisymmetric, or transitive.